Welcome to AI Paper Podcasts. Today we are diving into a really significant piece of research called MAI-UI, a foundational GUI agent for general grounding and mobile navigation.
Right. And if you've ever tried to get an agent to do something complex on your phone, like, say, book a flight and add it to your calendar, you know exactly where they just fall apart.
Exactly. This paper, though, it presents this whole family of models, from tiny ones that can run right on your device to these massive cloud versions.
And they're all designed to fix that brittleness. This work is pretty critical because it sets a new state-of-the-art right out of the gate. It's built on the Qwen 3 VL backbone.
And it's not just about being bigger, right? It's about being smarter.
That's the key. It comes down to four sort of core innovations. They've really improved the agent-user interaction.
So it can talk back to you.
Yeah, ask for clarification. Then there's something called MCP tool augmentation, scalable online reinforcement learning, and maybe most importantly for real-world use, a native device cloud collaboration system.
Okay, let's put some numbers on that just for a moment. On the big Android world benchmark, what kind of performance are we talking about?
So the biggest model hits a 76.7% success rate. That's huge. It's blowing past previous models like UiTars 2 and even beating out Gemini 2.5 Pro.
And what about that device cloud system, the efficiency part?
That's where it gets really practical. It boosts the on-device model's performance by 33%.
Wow.
While cutting the calls to the expensive cloud model by over 40%. It's a direct shot at the cost and privacy problems that are holding these things back.
Okay, let's unpack that. Let's start with the basic challenge this paper is trying to solve. Why are even the best GUI agents we have right now still so, fragile in the real world?
Well, the authors lay out four big open challenges. The first is what you just mentioned, agent-user interaction.
Right.
Most systems are built for end-to-end execution. You give a command, it tries its best, and then it either works or it fails.
Silently. But real instructions from people are messy. They're ambiguous. They're incomplete. An agent needs to be able to stop and say, hey, which address did you mean? Or, are you sure you want to delete this?
So it needs to be less of a robot and more of a collaborator.
Exactly. The second problem is this total reliance on UI-only actions.
Just clicks and swipes.
Just clicks and swipes, and when that's all you have, simple tasks become these long 20-step sequences.
And if just one of those steps fails because a button moved,
the whole thing breaks. It's incredibly brittle. That's what they call error propagation.
So how does moving beyond that help?
It's about introducing shortcuts, APIs. That's where their model context protocol comes in. Why click through 5 menus when a single structured API call can do the same thing instantly and reliably?
That makes perfect sense.
Okay.
So what was challenge number 3? That was the deployment issue, right? Cost and privacy?
Yeah, the native device cloud collaboration problem. Right now you have a choice. You can use a big, powerful, expensive model in the cloud.
Which has privacy issues. Right. Or you use a small, weaker model on your phone.
Yeah.
There's been no sort of intelligent middle ground, no seamless, privacy-aware way to hand off a task when the little guy gets stuck.
And the last one, the real world being messy.
Robustness to dynamic environments.
Okay.
Look, models trained on static screenshots are going to overfit. The second they see a real-world thing like a notification pop-up or a permission dialog or just a slightly different app version,
Fail.
they're done. They have no idea how to handle that unpredictability.
Okay, so let's dig into the solution for that deployment problem, because I think that's the most practical part here. The device cloud collaboration, or DCC, how does it work?
The whole idea behind the DCC is intelligent delegation. It's designed to keep everything on the device unless it absolutely has to go to the cloud.
So what's the mechanism?
The local agent on your phone actually has 2 jobs. It's the primary agent trying to do the task, but it's also acting as a trajectory monitor.
A trajectory monitor. So it's watching itself work. How does it know when it's messing up?
It's been specifically trained to look for red flags. One is seeing repeated actions with no progress.
Like clicking the same button over and over?
Exactly. Another is an explicit action failure from the OS. And the third is just general task deviation. It's sort of lost the plot and isn't doing what you originally asked.
That's brilliant. So it's trained to basically write its own bug report when it gets stuck.
That's a perfect analogy. Yeah. And when it detects a problem, it does 2 things. It decides if it needs help from the cloud, and crucially, it checks the screen for sensitive data.
Ah, so passwords, personal info.
Right. If it sees a password field, the cloud switch is blocked. Period. Privacy first. The task has to be resolved locally.
And if it does need the cloud, what does it send up?
It sends that bug report, basically, a concise error summary. It tells the big cloud model, here's where I got stuck and here's why.
And that context must be super important.
It's a 6.9-point increase in success rate just from adding that summary. It's a massive difference compared to just handing off the task cold.
So let's talk real-world impact. What were the final efficiency numbers on this DCC architecture?
Well, we mentioned the 33% relative performance boost for the local model, but for cost, it's huge. It reduces the number of calls to the cloud model by almost 43% compared to just running everything in the cloud.
You get the power of the cloud, but only when you need it.
Exactly. You get near cloud performance, but for a fraction of the cost and with privacy guardrails built in.
Okay, so if DCC handles deployment, let's talk about the agent's actual intelligence. This is where it goes from just tapping a screen to, actually solving problems. Let's get into that extended action space.
For sure. So they take the standard actions, click, swipe, type, and they add two really powerful new ones, a skeezer and a CP call.
Let's start with the skeezer. How does that change things?
It changes the entire relationship. It moves from you giving a command to you having a dialogue. So, if you say email the directions to Mike, but you forget to say what directions or who Mike is.
The agent doesn't just fail.
It doesn't fail. It issues an skeezer action and a question pops up. What destination should I use and what is Mike's email? You answer and it just picks up right where it left off.
That feels essential for any real-world use.
It absolutely is. Then you have MAI-UI call, the Model Context Protocol. This is the hammer for that brittleness problem we talked about.
This is the API thing.
This is the API thing. It lets the agent talk directly to apps or external tools like Maps, GitHub, you name it, using a structured call instead of fumbling around with the UI. And this has two main benefits.
Yeah, what's the first one?
Compression. Think about a task like comparing driving times for 3 apartments you got in a text. Manually, that's a nightmare of switching apps, copying, pasting.
I can feel the frustration just thinking about it.
Right. With MCP, the agent can issue one single MAI-UI call. It just sends the addresses from the messaging context over to the Maps context and gets the data back. No UI switching, no chance of error.
So it's compressing a dozen fragile steps into one robust action. And the second benefit, you said there were two.
Expansion. This is about bringing workflows that were really only possible on a desktop to your phone.
Like what?
Like searching a GitHub repository for the latest commits, summarizing them, and then emailing that summary. That's a heavy-duty task. A MAI-UI call gives the agent the structured access it needs to pull that off right there on your mobile device.
And I'm guessing the performance numbers back this up.
Oh, absolutely. On the Mobile World Benchmark, which is full of these realistic tasks, the big model got an 18.7-point boost on tasks that needed user interaction. And on MCP tasks, a massive 32.1-point improvement.
So these aren't just nice-to-haves, they're core to its success.
They're complete game changers.
Okay, so to build an agent this capable, you need a pretty intense training strategy. How did they get this level of robustness? Let's start with the data.
They use a really clever, self-evolving SFT pipeline. It's a closed loop where the data corpus and the model are constantly getting better together.
A closed loop.
Yeah, so they start with things like app manuals and some expert design tasks. The agent tries to perform them. But here's the key part, dealing with failure.
Right. Normally when a long task fails, you just throw that data away. It's a huge waste.
It is. So they use another model, an MLLM as a judge, to review the failed attempt. The judge looks at the whole sequence and identifies the longest string of correct actions before the mistake happened.
So if it failed on step 28 of a 30-step task, you don't throw away the whole thing.
You keep the first 27 correct steps, you save that valuable sub-trajectory, it drastically reduces data waste and lets the model learn from its partial successes.
That's so smart. Okay, so that's the data side. What about the environment side, online reinforcement learning? How did they scale that? Because GUI environments are notoriously resource hungry.
This was a massive engineering lift.
Nah.
They used containerized Android virtual devices, AVDs, orchestrated by a central manager.
So virtual phones?
Hundreds of them. They scaled it up to 512 concurrent instances running in parallel across a bunch of machines. It's like having 512 testers trying things all at once, constantly feeding the model new experiences.
And I assume scaling that wide had a direct impact on performance.
A huge one. Just going from 32 parallel environments to 512 gave them a 5.2-point gain in success rate. It proves that you need that incredibly broad exploration to build a robust agent.
So this is how it learns to handle all the random stuff, like pop-ups and permission dialogues.
Exactly. The online RL is what teaches it to be resilient. It sees an unexpected permission dialog, learns to dismiss it, and then gets back to the original task. It stops seeing those things as dead ends.
So with that architecture and training, the final numbers must be pretty impressive. Let's look at the benchmarks.
They are. We already mentioned the 76.7% success rate for the biggest model on Android World, which is state-of-the-art. But what's really telling is that their mid-sized 32B model gets 73.3%.
And that's still beating bigger models like Gemini 2.5 Pro.
It is. It shows the architecture itself is incredibly efficient. And on mobile world, the really complex benchmark, the big model gets 41.7%. The authors point out that this is competitive with these big, complex agentic frameworks that use things like GPT-5 as a planner.
But MAI-UI is just a single end-to-end model.
Exactly. It's all integrated.
And how does it do on the foundational task of just, clicking the right thing, the grounding?
Excellent. On M&Bench GUI, the 32B model hits 91.3%, another soda. And on the really high-resolution ScreenSpot Pro benchmark, it gets 73.5%, which actually edges out Gemini 3 Pro and Seed 1.8.
Okay, let's bring it all the way back to the smallest model. The 2B version for on-device use, how did it do?
This is where the story really comes together. The little MAI-UI 2B model achieves a 49.1% success rate on Android World.
Which sounds low, but what's the comparison?
The previous best on-device model was Ferret UI Lite 3B, which got 28.0%. So MAI-UI is a 75% relative improvement. It proves that this entire approach scales, creating genuinely useful models from the palm of your hand all the way up to the cloud.
So to wrap up, MAI-UI brings together 4 key things: a self-evolving data pipeline, scalable RL, that powerful MCP tool system, and the device cloud collaboration.
And together, they create a whole family of models that are state-of-the-art at every scale. It really feels like a roadmap for how to build practical GUI agents that work.
It's not just about making the model bigger, it's about making it smarter, more collaborative, and more resilient.
It's what bridges the gap between a high score on a benchmark and something you'd actually want to use every day.
So this really does point to a future where our phones could have truly autonomous agents, handling complex stuff across multiple apps, all while respecting your privacy.
It seems like we're finally on that path, but it does leave you with a question. If that device cloud system depends on the local agent constantly monitoring itself.
Right, that trajectory monitor is always running.
It's always running. So what's the hidden cost? What are the real-world latency and battery trade-offs of having that continuous self-monitoring running in the background, even for the tasks that never end up needing to call the cloud? That constant local oversight has to have its own price.